Now we're in chapter 1.5 and we're looking at different combinations of functions. So you're allowed to combine multiple functions with addition, subtraction, multiplication, division, any arithmetic operation. And so keeping domain in mind, since we're talking about functions, if there are any domain restrictions, you need to make sure that you list those domain restrictions. So first of all, we've got some just notation to look at. So you've seen this since, honestly, really since Algebra 1. So f plus g of x just means add f of x to g of x. You can subtract two functions, you can multiply them, and you can divide them. And it's a lot of times it's division where we get our first domain restrictions because you have to make sure that g of x doesn't equal 0. And so that might cause you to, you can either state that g of x can't equal 0, or a lot of times I will solve whatever g of x is, solve for x, and say x can't equal whatever. So something to keep in mind when you're working with multiple functions, let's just say we have two, we have f and g. When we're talking about domain of a combination, the first thing to do is consider domain of f, and then the second thing is consider domain of g. Like maybe f's domain is all real numbers, but g is like x can't equal 1. So then in our final answer, we have to carry through those domain restrictions, whatever they are, and then consider any sort of overlapping domain. For our final domain of combo. And we'll get into this more, but that could be like if f is x is greater than or equal to 0, and g is x can only be less than or equal to 10, well then our domain is 0 to 10 overall to satisfy both of them. Okay, so that was just an example. So looking at these two functions here, we've got f of x is the square root of x minus 3. G of x is the square root of 25 minus x squared. Find each combination and state the domain for each combination's function. So let's take a look before we get into these combinations. Let's just remind ourselves about these domains. We have a square root function where x is going to be anything greater than or equal to 3 for f of x, right? Because x minus 3 stays greater than or equal to 0. We should recognize this square root of a difference of squares. Remember, this is your semicircle. This one has a radius of 5, square root of 25. So g's domain is that x should be anything between negative 5 and positive 5. So when we combine these two, we're going to have to think about, well, really our domain is going to be anything bigger than 3, but smaller than 5. So I'll talk about that in a minute. Find the function for f plus g of x. So that just means f of x plus g of x. Remember, with square roots, you're not allowed to combine square roots together unless they're the exact same expression, and then you would just be adding the numbers in front. So like you're allowed to do radical 3 plus 4 radical 3, that's 5 radical 3, but I'm not allowed to combine these. I can't do radical 3 plus 4 radical 2. There's nothing to simplify that further. So this is as far as the function goes. So that's the easy part. Come up with the function. Okay, there's f plus g of x. The domain piece, again, we used f and we used g. So sometimes it helps to draw these on a number line. Here's 3. Here's the domain for f, anything greater than or equal to 3. G's domain is anything between negative 5 and positive 5. The domain of values that I'm allowed to plug into this combination function and keep both pieces defined is just the overlapping section between 3 and 5. So you can use interval notation, or we will often see it listed out in inequality notation when we're looking in textbooks or on an AP exam. So I come up with my new combination and I state the domain. Every time you come up with a new equation in terms of x, you're not just evaluating, you need to state what the domain is, even if it's all real numbers. All right, so g divided by f of x. So first of all, let's just write down what that would be. G of x is on top, f of x is on the bottom. We're not going to rationalize denominators if it's not just a numerical denominator, so I'm not going to worry about the fact that I have square root of x minus 3. You are allowed to make this like a square root on top and bottom. You are allowed to merge it all together. That doesn't really help me in any way, but I would take either one of those. And then what about the domain? Well, we're still using the same two functions, but now x minus 3 is not, it's in the denominator now. So x can't actually equal 3. X minus 3 needs to just say greater than 0. So x should be greater than 3. And then because of the square root of 25 minus x squared, that's still saying x can be anything between negative 5 and 5. So we just have this slight adjustment to make where 3 is just less than x, which is less than or equal to 5. So slight adjustment because the square root of x minus 3 wound up in a denominator, and we don't want to divide by 0. For f times g, so when you multiply two radicals together, you don't have to have the same radical, right? Like radical 3 times radical 2 is just radical 6. You're allowed to multiply those together. So in this case, I can say it's the square root of x minus 3, the quantity, times 25 minus x squared, the quantity. You could FOIL this whole thing out. I think the only reason I would do that is if I were looking for an answer in multiple choice. So I could FOIL it together. I'm still going to say that I used these original two pieces, and so x still needs to remain between 3 and 5, and 3 and 5, 3 is back in our domain because it's no longer in a denominator. Again, we're going to talk about polynomial inequalities down the road in chapter 2. So I could solve this with a polynomial inequality, but because we're just building new functions out of individual functions, we can still just consider their overlap to figure out domain. Evaluate using the function above. Show two ways to get the answer. So I prefer one way over the other. I'm going to show you both just to kind of show you what's going on. So use these same f of x and g of x and show two ways to get the answer. So one way to get the answer is you've gone through the trouble of finding f times g of x. It was the square root of x minus 3 times 25 minus x squared. And so then after you figure out what that equation is, you can figure out f times g of 4 by plugging 4 in. 4 minus 3 is 1. 25 minus 16 is 9. The square root of 9 is 3. Okay, so this is one way. The alternative method is to say, well, f times g of 4 is equivalent to f of 4 times g of 4. So f of 4 was the square root of x minus 3. So square root of 4 minus 3 is square root of 1. G of 4 is the square root of 25 minus x squared. 25 minus 16 is 9. 1 times 3 is 3. For this problem, you're almost doing the same thing anyway, because with the multiplication, I didn't have a lot of extra work to do, but there are basically two ways to show it. Get the equation first and then plug in, or plug into each part and then perform whatever operation it tells you. This is the method I usually prefer. It's almost always faster. Sometimes finding the equation first is a bit cumbersome, or it's easier to make a mistake. G divided by f of negative 2. So show two ways to get the answer. I'm going to start with way number 2. So this is equal to g of negative 2 divided by f of negative 2. G of negative 2 is the square root of 25 minus negative 2 squared is 4. F of negative 2 would be the square root of x minus 3 square root of negative 5, we run into a problem right here. This is imaginary, right? We are going to talk about imaginary numbers, by the way, but when we're listing out domain, we're listing x values that ensure that the function produces real numbers, graphable numbers, right, in the real coordinate system. So there's no solution to this because x equals negative 2 isn't in the, what did we say, the parentheses 3 to 5 domain. Remember back here, we said for this g divided by f function, you can't plug in anything outside of this domain, so negative 2 doesn't work. All right, so I'm not going to show a second method on that, but the second method would show you pretty much the same thing anyway, finding g divided by f, which was this, and plugging into that. Okay? Excuse me. F plus g of negative 5. Again, I'm going to focus on method 2. Think of it as f of negative 5 plus g of negative 5. Your other option is to say, I'm going to plug negative 5 into this f plus g of x equation. But again, for these examples, this is kind of a poor choice of problems because the two methods look pretty close to the same thing. So anyway, I'm just trying to hammer home the point that you can do this. So f of negative 5 is the square root of, oh wait, this shouldn't be negative 5. This should be positive 5. Negative 5 is not in the domain. Sorry, that's a typo on my paper. I think I've fixed it for your notes. Let's do 5. 5, not negative 5. I don't want another no solution. So if we plug in 5 into f, we get square root of 5 minus 3 plus the square root of 25 minus 5 squared, square root of 2 plus square root of 0, which is just square root of 2. Remember, square root of 0 is 0. All right, so that's evaluating combinations of functions. Composition is where things can get a little bit trickier. So a composition is not really an arithmetic operation. It's not addition, subtraction, multiplication, division. It's plugging one function into another function. We call that composition. So we have this little symbol here. This little open circle means composed with. I would read this as f composed with g of x, or f of g of x. That's fine too. And domain is usually the tricky thing. So I've written out a few things for domain. We've got to make sure that the domain of our composition is the set of all x that satisfy the domain of g, and then that also has to be able to be plugged into f. So it's confusing to like explain it with that sentence, so I wrote out these steps here. So when you're doing domain for a composition function, first state the domain of the inner function. So the, f of whatever's in here, this domain. If there are any restrictions, those restrictions have to make it into the final answer. And then you do your composition and you take a look at your final answer. And if there are any extra restrictions, like maybe now x can't equal 2 or something, that domain restriction has to make it into the final. So when we look at those two pieces, we look at the overlapping domain. So if there's anything that they have in common, then that's our final domain. Okay, so f of x is the square root of 6x. G of x is 3 times x minus 2 squared. Find each composition. State the domain of the composed function. F composed with g of x means f of g of x. I suggest writing in what g of x is before you start actually plugging into the function. So that means f of 3 times x minus 2 squared. And then I pause right here because I don't want to forget about domain. This is a quadratic function. There are no restrictions on the domain so far for the inner function. So right now, my domain for the composition, all real numbers. I need to keep in mind for f of x that we can only have values that make 6x greater than or equal to 0. Now, when I plug that expression into f of x, instead of square root of 6x, I get square root of 6 times 3 times x minus 2 squared. 6 times 3 is 18. Square root of 18 times x minus 2 squared. Okay, now we have to be very careful here when we're square rooting an expression with an x in it. First of all, we're allowed to separate this. This is the square root of 18 times the square root of x minus 2 squared. So square root of 18 is 3 radical 2. And then here's where we have to be careful. The square root, I want to make an extra note here. Important. Before I get to my final answer. The square root of x squared is not x. The square root of x squared is the absolute value of x. Because, for example, I know I've done this before in a different video, but they might have been out of order, so we may or may not have seen this before. Plug in negative 2 in for x. So this is when x equals negative 2. Plug that into the square root of x squared. Order of operations says to square this value first, and then take the square root of 4. So my answer is not x. It's actually the opposite of x, right? X was negative 2. My answer was absolute value of negative 2. If you plug in x equals 2, yes, my answer is x, but that's only true if x is positive. So when we plug in negative numbers, we have to be able, we don't get negative answers out of a square root. So the way to get around that is every time you square root an x squared, you're simplifying that to absolute value of x. Okay, that's going to be important down the road, and it will show up for our AP Pre-Calc stuff. With that in mind, the square root of x minus 2 squared then is not just x minus 2. It's the absolute value of x minus 2. Okay, so 3 radical 2 times the absolute value of x minus 2. Now, do absolute value symbols have any restrictions on them? Think about an absolute value graph. No restrictions, right? And no restrictions on our inner function. So this is still all real numbers for our domain. Now, if we switch the order of composition, that matters. So this is g of f of x, which is g of the square root of 6x. Plug that into your equation. So we get 3 times, instead of x, it's the square root of 6x minus 2 squared. All right, now let's go back because I got ahead of myself. Before I plugged that in, I should have made a note of my domain. This is a square root function. 6x needs to stay greater than or equal to 0, which means x just needs to stay greater than or equal to 0. So this needs to make it to my final answer as far as domain restrictions. Look at the final answer. There's no new expression here. Like this is overall raised to a second power, no issues there. I still have the square root function. So it's still just that x needs to stay greater than or equal to 0 for this graph to exist. And you can test all of these, by the way. If you graph your original unsimplified function, like if you type it in exactly as it's shown right here or right here and you don't simplify it at all, you should see that the graph either exists for all real numbers or exists just starting at 0 and going to the right, etc. You can also compose a function with itself. So f composed with f of x means f of x. That means f of the square root of 6x. And careful with this, that means the square root of 6, instead of x, we're putting in the square root of 6x. So that looks really weird. I would like to switch to exponents. to try to simplify this, because a square root and a square root looks very strange. By the way, x greater than or equal to 0 so far. Okay, let's think about what this is. A square root, the big one on the outside, is the same as raising something to the 1/2 power. Okay, and then we have 6 to the first underneath there. This 6 is to the 1/2 power, and this x is to the 1/2 power. And remember, with exponents, we can add our exponents. So 6 to the first times 6 to the 1/2 is 6 to the 1/2, or 3/2, times x to the 1/2 raised to the 1/2. And then when you do power to a power, you multiply your exponents. So 6 to the 3/2 raised to the 1/2 power, I multiply 3 over 2 times 1 over 2, I get 6 to the 3/4, x to the 1/2 times 1/2, 1/4. Now you can leave your answer like that, or you can translate it back into its root form. They're both under a 4th root, so that's convenient. 6 to the 3rd, what is 6 to the 3rd? Feels like one I should know, but we can also just do some quick math. It's 216. The 4th root of 216x. And remember, way back from your inner function, x needs to stay greater than or equal to 0, which is still true for this even root, by the way. We have an even root. 216x should stay greater than or equal to 0 as well. And so that made it into our final answer. All right, just like we were allowed to evaluate functions where we were using arithmetic operations, we're also allowed to plug numbers into compositions. These are the problems where it's definitely better. I'm going to say again, show 2 ways to get the answer. If you haven't gone through all the trouble of already finding the combination or the composition function, then you might as well just use the numerical route. But one method for finding f composed with g of -3 is to say, well, f composed with g of x, that was equal to 3 radical 2 times the absolute value of x minus 2. And then I can evaluate that at -3. 3 radical 2 times the absolute value of -5. So that's 5. So 15 radical 2. If I didn't go through all this trouble, though, maybe I haven't found the composition. Like maybe part A was just evaluate. It wasn't find the actual equation. So the second method is the numerical method, which I prefer. F composed with g of -3 means f of g of -3. So take it in pieces. First find g of -3. So reminding myself what g was. 3 times x minus 2 squared. So 3 times x minus 2, -5 squared. So that's f of 3 times 25, f of 75. And then plug 75 into f of x. F of x is square root of 6x. Square root of 6 times 75. Now, should I bother multiplying 6 times 75? The answer is no. If you're trying to simplify radicals, if you have numbers that are going to multiply out to be large, and then you have to try to dig out perfect squares, it's best to just start factoring them right now. Break these down into their prime factors. 6 is 3 times 2. 75 is 25 times 3. 6 times 75 then can be 2 times 3 squared times 5 squared. That shows you what perfect squares can pull out. 3 times 5. Radical 2 stays. 15 radical 2. Now, red was less steps, but that's only because I already did these previous steps. So add these 1, 2, 3, 4, 5 steps to what I did before I plugged in -5, and you can see both methods would take similar amount of time. For number 11, I'm just going to show the numerical method. So find g of f of 2. You always start on the innermost piece of a function. So find f of 2. F was square root of 6x. Square root of 6x, 6 times 2 is 12. So g is, or this is now g of 2 radical 3. G's equation is 3 times x minus 2 squared. 3 times 2 radical 3 minus 2 squared. Now, we could leave it like this, or maybe we're looking for our answer in a multiple choice on an AP test. So remember, this is just a binomial that you can square. 2 radical 3 times itself becomes 4 times 3. 2 radical 3 times negative 2 is minus 4 radical 3, and you double that, minus 8 radical 3. 2 squared is plus 4. 12 times 3 is 36. Minus 3 times 8, 24 radical 3, plus 12. 48 minus 24 radical 3. If you're not looking for a multiple choice answer, I would leave it like this. If they want you to simplify further in a free response, they might guide you more in the directions. Although with this being the first year for the test, that's not 100% clear yet. All right, so f composed with f of 6. Let's do this numerical method. That means f of 6. F of 6 is the square root of 6x, so square root of 36. Square root of 36 is 6. Plug 6 into f of x, you get square root of 6 times 6 again. Answer is 6. Okay, here's an AP problem. And let's see, I'm not sure if we need, I think we can use our calculator for this one. So the number of bacteria in a refrigerated food is given by this function. Here's the domain, where T is the temperature of the food in degrees Celsius. When the food is removed from the refrigeration, the temperature of the food is given by this function, 4T plus 2, and this is for the hours between 0 to 3. Part A says, find the composition N of T and interpret its meaning and context. Okay, so let's just find the composition first. N of T. So we're plugging, that really means N of 4T plus 2. So that's 20 times 4T plus 2, the quantity squared, minus 80 times 4T plus 2, plus 500. And remember, the domain for T was between 0 to 3. That was given to us. So that still has to carry over here. And again, on an AP test, I'm not sure if you would get full credit for the equation and not the domain restriction, or if you have to have both. So better to practice both. Now, I'm not going to bother simplifying this, especially if this is a calculator problem. Oh, interpret its meaning and context. So what does this mean? T is the time, lowercase t is the time that the food has been out of the refrigerator, and N is still counting the number of bacteria, right? So this is a model to show the number of bacteria in the food at T hours removed from fridge. And I'm just going to say for 0 less than or equal to T, less than or equal to 3. Part B says, find the number of bacteria in the food when T equals 2 hours. So now find N of T of 2. I don't want to just say N of 2 because technically this model is not N of T, it's N of T of T. So weird technicality stuff. Or I could say, if I don't want to say n of 2, I could just say n of, when you plug 2 in, you get 10, right? So that's the same as n of 10. But honestly, at this point, we can just plug into our calculator. So now we can, if this is non-calculator, let's see. Yeah, this is going to be calculator. So if this is non-calculator, I would go through and like do the math. But if it's calculator, I want to show you this if I haven't done this before. Let's clear out the old equation, turn off the plot. So type in this model that you created, n of t of t. So 20, use your parentheses, all that. Just getting this typed in. Okay, and I don't really need to graph this. I can. Why don't we just graph it just because we're going to have to down the road. The window should be 0 to 3. And then we're going to zoom fit, which is option 0. Here's the function. We want to find n of 10, so you can do this a couple of ways. Well, let's see. Sorry, we want to find n when t equals 2. So, sorry, not n of 10. Let me just get this out of here. I want to find n of t of 2. So when t equals 2, we could say find second trace, find the value at 2, right? 1700. Or we could on our screen, on our home screen, we've got the equation in y1, so we didn't have to graph it. We could say alpha trace y1 of 2, and it finds it on my home screen too. So you can use function notation on your home screen if you have the equation typed into y equals. So 1700 bacteria. Do we need to show the work for plugging that in? If it's non-calculator, I would think yes. Otherwise, I think the answer would suffice. And then for part C, find the time when the bacteria count reaches 2000. So this is saying, when is 2000 equal to n of t of t? If you'd like to write out the equation for n of t of t, you can. But this is where, again, if I'm on my calculator, I just need to show the equation for the AP exam, show the equation that I'm solving, hop over to my calculator, go to y equals, type in 2000, just press graph because you already did the zoom fit thing. So it's the time where these two graphs intersect. So second trace, intersect, option 5. And this is just saying first curve, second curve. So if you have more than 2 equations graphed, they want to make sure they're picking the right 2. So you just press enter, enter, and guess. So rounded to 3 places, 2.222 is our t. And that's measured in hours. So there will be about 2,000 bacteria if the thing's been sitting out for 2.222 hours. All right, so that's an example of an AP free response question that we could have regarding these functions. All right, that's it for today's notes. Our homework tonight is in the book, and please come to office hours if you have any questions.